Our first lesson in the second half of our first unit together deals with inductive reasoning. Inductive reasoning. So we're going to learn what inductive reasoning is, and then we're going to learn how we use it all the time to make conjectures. We're going to learn what conjectures are as well. As we define these terms, we'll sort of expose how this is something that you do all the time. We're going to contextualize some of this thinking in terms of, obviously, our class here in geometry. So inductive reasoning is simply reasoning based on the patterns that you observe. So you take a look at reality, you see the world around you, and then you think about what you see. And the thoughts that you have about what you observe let you have opinions about the world around you, let you make predictions about what may or may not happen next, etc. And so we're going to focus on inductive reasoning. For example, let's see if we can describe the patterns that we see here. So for example, I see 5, 10, 15, 20, 25. We probably can predict, we're going to talk about that next, what is going to come next, but can we describe what we're actually seeing? Because we use that thinking to make our prediction, but first we have to outline what the pattern actually is. So for this, I would say that we simply add 5 each time, right? It's 5 plus 5 makes 10, plus 5 makes 15, plus 5 makes 20, etc., etc. So our pattern here is that we add 5. Over here, this one might be a little bit different. 384, 192, 96, 48. These numbers might be a little bit big, so that we can't really tell maybe what that pattern is just using our times tables or whatnot. However, as we get smaller here, we can kind of say like, oh, this is like we divide by 2 and we divide by 2 and we divide by 2. So is that really what's happening? And you can test that using your calculator. But really what's happening is we're dividing by 2 or multiplying by 1/2. Right? Multiplying by half and dividing by 2 are the same thing, right? So divide by 2, or multiply by 1/2. If you gave either of those answers, that would be an appropriate way to describe that. You would never have to double that description. Just give it one way or the other. All right? And then here, this one's maybe a little more complicated. To see what comes next in the pattern, we might be able to predict that, but can we describe what's happening? Well, really what's happening is we're subtracting 1, and then we're subtracting 2, and then we're subtracting 3. So we're subtracting 1 more each time that we go through this pattern. As we go to the next iteration, we'll subtract 1 more than we did before. So the goal here is, can we describe the pattern that we are observing? Sometimes when it's numeracy skills, where we are adding the same amount or subtracting different amounts or dividing by the same number, it's kind of straightforward. Other times our patterns are a little more difficult. Maybe there are letters or words or names that require that we have an understanding of other content knowledge, all right? But that pattern is still true. Now we know that George Washington was our first president, but Thomas Jefferson was not our next president, right? He was our 3rd president. And then Lincoln was like our 16th president. So is there a number associated with the name, or is there something else? For example, like we have folks on here that we may not recognize that these are actually people that are on American money, right? So we have the $1 bill, the $2 bill, the $5 bill, the $10 bill, the $20 bill, the $50 bill, all right? And so these are people that are on American paper money is maybe how we would describe it. This one right here, this is a series of letters. Can you tell what this pattern is? I'll tell you in a couple slides, but see if you can fill that in. Or maybe our pattern involves geometric figures that are drawn or divided or subdivided or rotated. And we can sort of describe what's happening in that, well, this was cut into with 1 dividing diameter that cut into 2 equal parts. This was cut with another diameter that cut now into 4 equal parts. This was cut with a 3rd diameter. So the next one would have 4 diameters drawn in. All right, and so we can kind of make that prediction having another dividing diameter drawn through the circle. All right, maybe is how we describe that pattern. So inductive reasoning is describing the patterns, thinking about what we see, all right, which is sometimes harder than the actual conjecture portion. A lot of times, a student or even a young child can say what will happen next, but maybe it's difficult to describe what is actually happening. All right. Here we're going to try to do both, and we're going to try to keep that in tension with each other and in tandem with each other so that we can make a conclusion using that inductive reasoning. So if we are adding 5 each step, then we know that the next term or terms in the sequence will be 30, 35, 40, etc., etc. If we're multiplying by 1/2, then the next number would be 6, and then 3, and then 1.5, and then 3/4. And so we can predict what comes next by multiplying by 1/2 or dividing by 2 every time. All right, so predict what comes next here. You fill that one out. And then we'll go to the next slide so you can see what those patterns were. You don't have to rewrite this, right? You've already written it once in example part 1. So part 2, oh, these are the first letters of the counting numbers. 1, 2, 3, 4, 5, 6, 7. And so the words are spelled 1, 2, 3, 4, 5. And so these are the first letters of the word representing the numbers that we write. And so we can predict what comes next. 10, 11, 12, 13, 14. The next one will be 15, 16, 17, 18, 19, etc., etc. So we can kind of continue that. These are the people that are in our American paper money. After the $50 bill comes the $100 bill, and so Benjamin Franklin's on there, etc. And maybe, like I said, we would have 4 diameters drawn here. So 1, 2, 3, 4, and those are cut into equal eighths of the circle. All right. So making a conjecture, we obviously want to make correct conjectures, but sometimes we'll make a conjecture and it's wrong. All right, we'll say, I think that this is what comes next, and in reality, we didn't predict that correctly. And so we'll have to be corrected, maybe have a little bit of humility. Other times, we'll be given a prediction. We'll have to explain why it's false, or that it's false, and explain what the pattern actually is and what the next terms in the sequence may be. Continuing this thought, though, about making a conjecture, let's think about making a conjecture using the sum of the first 30 odd numbers. Now, this is a little bit tricky because some of us want to just do all of the work. And my position is that if we think harder, we get to do less work. All right? And that's kind of a long haul, marathon idea for the course of this semester, because as much as we might enjoy the work that we get to do, and we might just find comfort in, the rote repetition of doing 50 exercises on a classwork assignment, we're just not going to do that. We don't have the time or the energy for it. So likewise, I'm not going to take 1 plus 3 plus 5 plus 7 plus 9 plus 11 plus 13 plus, I'm not going to do the first 30 odd numbers, add them all up and find out what the sum is. That is a waste of my time, and it's probably a waste of your time as well. But what we are going to do is think about what we see. So if I'm going to make a conjecture about these first 30 odd numbers, then I want to try with maybe a handful of the odd numbers. And let's see what we observe when we see what those sums actually are. So 1 is just 1, but 1 plus 3 makes 4. And 1 plus 3 plus 5 makes 9. And 1 plus 3 plus 5 plus 7 makes 16. Now, if you know numbers well, which is one of those things that kind of comes out of doing arithmetic by hand, or just having an understanding of how these numbers interact with each other, you would notice that these 4 numbers are special. And the next one's special as well. The next one's 25, and then 36, and then 49. Those should be special numbers in your brain using what's called number sense. All right, that's not something that you're taught. It's just something that is fostered maybe and developed over time. All right, so if you don't know the quick knee-jerk answer to this, then it's probably okay. It's probably just a symptom of maybe having some arithmetic skills that you're still working on. But here you should notice that this is a list of perfect squares. All right, 1 squared, 2 squared, 3 squared, 4 squared, then 5 squared, 6 squared, 7 squared, etc. So we can recognize that of this set, every one of those sums is a perfect square. And we can maybe make some other predictions. Okay, what would be the next term in the sequence? Okay, 25. Oh, that's 5 squared. Oh, 36. Oh, that's 6 squared. So our conjecture for this, and this is what you're going to write down. I'm not going to write it down on the board. You're going to have to listen and you're going to have to write this down. About the sum of the 31st odd numbers. The sum of the first 30 odd numbers will be a perfect square. More specifically, if I'm going to draw in there, if the first 1 is 1 squared, and the first 2 of them add up to 2 squared, and the first 3 add up to 3 squared, and the first 4 add up to 4 squared, what are the first 30 going to add up to? See if you can tell me what that number actually is going to be. All right, see if you can do that without doing all of the work, but doing the thinking. All right, see if you can give that answer. Okay, continuing on, counterexamples. Sometimes we will have a conjecture or read a conjecture and it's wrong. All right, and we need to explain why it's wrong. And a way that we can do that is we can provide a situation where we show that the conjecture is false. All right, where we can show that our conjecture is false. So here's an example of why we might have a situation where we would use a counterexample. The first odd prime numbers are 3, 5, and 7. So someone not you, of course, would look at that and say, oh, well, 3, 5, 7, I bet the next prime odd number is 9, all right, because they're just saying the next odd number. Well, we know that this is false, all right? So we can kind of go two ways. First is to explain why 9 is not. Explain not 9. And the way that we would show that is we would say 9 is 3 times 3, right? It's not a prime number. It is divisible by a number other than 9 and 1. And so we would show why it's not 9. The other way is to do a counterexample. And this is a little bit silly for this particular example. And the counterexample for not 9 would be to say the next prime, whoops, handwriting, the next prime is 11. And you're actually saying, well, 9 is not the next prime, 11 is. You're providing the example that actually correctly answers the prompt. All right, you're accurately and correctly predicting what the next thing is. Counterexamples, we're going to add a little more teeth to that as we move through this conversation in this unit. Okay, it's going to take on another level of understanding of showing that our conjecture is not true. We're still giving the next prime number, but it's not the number that we were told, right? It's the number that it actually is, all right, 11. All right, so here's another way in which we can show another counterexample. So here we have 5 times 5 is 25, 5 times 3 is 15, 5 times 7 is 35. So someone who is learning multiplication, maybe in 2nd or 3rd grade, might say, it seems to me that the product of any number and 5 is going to be another number that ends in 5. All right, and so we would give a counterexample showing that we are taking any number times 5, but we are getting a product that does not end in 5. This would be a counterexample. This would be a way to demonstrate what comes next, all right? Or not what comes next necessarily the pattern, but what is the product of any number and 5 and how it is not always a number that ends in 5. Now, you could provide additional explanation, but the extra explanation is unnecessary. And sometimes students want to overdo it. They want to overcook, and they want to say, oh, well, it appears that actually it's the product of 5 and any odd number that give us a product of of a number ending in 5. And it's like, okay, that's true, but that's not a counterexample. So if we're going to give a counterexample, then we will give an example where we're still doing any number and 5, multiply, but our answer is not something that ends in 5. All right, the product is not a number ending in 5. So we still have the beginning part true, but the end part is different from what our conjecture stated. All right, that's a little bit hard to wrestle with, but that's the way that it is. All right, so in summary, inductive reasoning will lead us to make conjectures. All right, we will observe patterns, and that will lead us to predicting what comes next. We can use specific examples that will then be generalizable. That's not always true, but it's a good thing that we can do with inductive reasoning. It doesn't always work. It doesn't always give us a true conjecture, but hey, it's an idea. It does not necessarily show that a conjecture is true, but we can always disprove a conjecture by providing a counterexample. It's really tough to show that something is true, that a conjecture is true in every possible scenario, and that's kind of the punchline to this semester. That's where we're gonna get by December. All right, so be very patient with yourself as you learn about inductive reasoning and as you work through this difficult semester of geometry. Hopefully, you are now able to use inductive reasoning to make conjectures.